Would you get a solar flare? The level of charged particles can be so high it can short-circuit the electronics of satellites. When it reaches Earth, prepare for an extraordinary event. Neil deGrasse Tyson just shared the news that the Sun has unleashed one of the most massive explosions ever recorded, an X-28 class solar flare. This marks the most intense flare in 17 years, capturing a moment of both wonder and concern. But how does this celestial event impact us on Earth? What happens when a surge of solar energy, thousands of times more potent than usual, reaches our planet and influences our daily lives? Join us as we delve into this solar spectacle, unraveling the mysteries of this astonishing occurrence and its implications for our technologically driven world. Solar flares, the Sun's dramatic displays of energy, are a natural phenomenon stemming from the Sun's corona, its outermost layer. These flares are a byproduct of the Sun's intricate magnetic field, where magnetic field lines can twist and snap, releasing an immense amount of energy that heats the solar atmosphere to millions of degrees. This process accelerates charged particles, predominantly electrons and protons, through magnetic reconnection, transforming magnetic energy into kinetic and thermal energy, resulting in an intense burst of X-rays and plasma, the creation of solar flares. But what happens when an immense solar flare, like the X-28 class, directly targets Earth? Solar flares are classified based on their brightness and X-ray wavelengths into two main classes, M-class and X-class flares. M-class flares are medium-sized events that can cause brief radio blackouts at the poles and minor radiation storms. On the other hand, the more formidable X-class flares are the largest explosions in the solar system, capable of creating planet-wide radio blackouts and long-lasting radiation storms. The energy released in these flares is staggering, and their occurrence is closely tied to the solar cycle, an approximately 11-year cycle where the Sun transitions from a solar minimum to a solar maximum. This cycle plays a crucial role in predicting solar flares and understanding their potential effects on Earth. Agencies like NASA and NOAA are at the forefront of monitoring solar activity and predicting solar flares. Satellites such as the Solar Dynamics Observatory enable real-time detection of flare occurrences, while the NOAA Space Weather Prediction Center provides forecasts and alerts using a network of ground and space-based sensors. On December 14, 2023, the Sun experienced a significant solar event, emitting an X-28 class solar flare, one of the most intense categories. This event marked a pivotal moment in solar observation, being the biggest flare in the last 17 years. The classification of X-28 places this solar flare among the most powerful types. To grasp its magnitude, X-class flares are the largest explosions in the solar system, and an X-28 flare indicates one almost 3 times more intense than the baseline X-1 flare. The energy released in this event is immense, equivalent to that of a billion hydrogen bombs. Such powerful solar flares can have far-reaching consequences, impacting satellites in orbit, disrupting radio communications, and causing changes in the Earth's ionosphere, affecting GPS and other navigation systems. The event of December 14th was meticulously captured and monitored by various space agencies and observatories, including NASA's Solar Dynamics Observatory. This observatory continuously monitors the Sun, providing valuable data that aids in predicting and understanding solar activities. The occurrence of such a potent solar flare during the current solar cycle, which began in 2019, was unexpected, adding an element of surprise to our exploration of the Sun's dynamic behavior. The solar cycle, spanning approximately 11 years, goes through phases of high and low solar activity known as solar maximum and solar minimum. The ongoing cycle has been relatively calm, featuring fewer sunspots and lower solar activity. The unexpected flare on December 14 serves as a surprising and notable event, emphasizing the dynamic and unpredictable nature of our Sun. This solar event underscores the importance of continuous monitoring and studying solar activity. Valuable insights and data from this flare contribute significantly to our comprehension of solar activities and their impacts on Earth. This information aids in developing more effective prediction and mitigation strategies for future solar events. The December 14, 2023 solar flare, classified as X-28, disrupted human systems, showcasing our vulnerability to solar activities. Immediate effects were observed on radio communications, power grids, and satellites, highlighting the profound implications of such solar events on our technology-dependent world. Radio communications were particularly affected, as solar flares emit intense bursts of electromagnetic radiation, ionizing the Earth's upper atmosphere. This disruption led to interruptions in high-frequency radio communications, impacting aviation, maritime, and ham radio communications. Satellite operations faced threats due to the intense radiation and energetic particles released during the event. Geostationary and polar orbit satellites were especially vulnerable to damage, ranging from temporary malfunctions to permanent failures. The solar flare's potential impact on power grids raised concerns. Geomagnetic storms induced by solar flares can create electrical currents in the Earth's magnetosphere and ionosphere, potentially overloading transformers and components of the electrical grid. In addition to disruptions, the solar flare created captivating auroras visible at lower latitudes. Social media buzzed with user-generated content capturing these stunning displays, showcasing widespread visibility and public fascination with the phenomenon. NASA's Solar Dynamics Observatory, launched in 2010, plays a crucial role in understanding and predicting solar activities. Equipped with sophisticated instruments, it captures high-resolution images of the Sun in various wavelengths, providing invaluable data for studying solar behavior. The observatory's instruments, such as the Atmospheric Imaging Assembly and the Helioseismic and Magnetic Imager, offer detailed insights into the solar atmosphere and magnetic field. Observations from the December 14th flare enhanced understanding of its formation and potential impacts on space weather. Continuous monitoring by the Solar Dynamics Observatory allows scientists to observe solar phenomena in real time, aiding in forecasting future solar events. Predictions are critical for safeguarding technology and infrastructure on Earth from the effects of intense solar radiation. The observatory's contributions extend beyond immediate space weather prediction, playing a key role in understanding the solar cycle's influence on space weather over the long term. The Solar Dynamics Observatory has been tracking the Sun's activity for years, helping scientists identify patterns preceding various solar phenomena. This long-term data is vital for understanding how the solar cycle influences space weather and, consequently, Earth. The observatory's findings enrich our broader scientific understanding of the Sun, offering insights into its magnetic field, internal dynamics, and the processes behind powerful phenomena. Collaborating with observatories and space weather monitoring agencies, like NOAA's Space Weather Prediction Center, the Solar Dynamics Observatory forms part of a global network sharing data and insights. This collaboration enhances our collective ability to prepare for and respond to solar activities. Renowned astrophysicist Neil deGrasse Tyson provides unique insights into the recent X-28 class solar flare, connecting it to broader concepts in astrophysics and space exploration. Tyson's ability to demystify complex concepts offers a nuanced understanding of the Sun's behavior and its implications for Earth. Tyson likens the Sun's activities to a pot of boiling oatmeal, vividly capturing the dynamic nature of our star. Solar outbursts like the recent significant solar flare provide a critical lens to study the Sun's inner workings. Tyson highlights the Earth's magnetic field's crucial role in protecting against harmful solar particles, deflecting them to create stunning auroras. However, Tyson notes that larger flares, like the recent one, can penetrate further, potentially disrupting electrical grids and overwhelming transformers. He emphasizes the vulnerability of our satellite infrastructure, crucial for communication and technology, to solar flares. Tyson stresses the importance of radiation-hardened electronics to safeguard these assets. Addressing a misconception, Tyson clarifies that the perceived increase in solar activity results from improved observational capabilities. Advanced technology allows more detailed and frequent observations, leading to better reporting and understanding of solar phenomena. Tyson's insights extend beyond the immediate effects on Earth, prompting contemplation of broader implications in the context of astrophysics and space exploration. These solar events provide windows into our universe, offering valuable information for advancing scientific knowledge and preparing for future challenges in our technology-reliant world. The recent solar flare is not an isolated event in history. Throughout history, notable solar flares, like the Carrington event in 1859 and the Great Geomagnetic Storm in 1921, impacted Earth, causing widespread disruptions. The March 1989 geomagnetic storm in Quebec led to a major power outage, and the 2013 Halloween solar storms were among the most intense of the space age, showcasing the powerful impact of solar activities on Earth's technological infrastructure. These historical events underscore the importance of understanding and preparing for the potential consequences of intense solar activity. The auroras created by these solar storms were visible much farther from the poles than usual, reaching as far south as Texas and the Mediterranean, highlighting their exceptional strength. These events showcase the immense power of solar activity and its potential to disrupt modern technology and infrastructure, underscoring the importance of continuous monitoring and preparedness for such solar events. While our recent solar flare has captured attention, let's expand our focus beyond our solar system to explore how similar stellar phenomena occur in distant stars and their potential impact on surrounding planets. Recent research has turned to distant stars like TRAPPIST-1, a red dwarf star about 40 light-years from Earth, known for its unusual solar flare activity. The James Webb Space Telescope, JWST, has been crucial in observing these flares, using its advanced infrared capabilities to detect details that were previously invisible, offering new insights into the physical processes on TRAPPIST-1. Observations have identified 4 distinct solar flares from TRAPPIST-1, varying in intensity, duration, and emitted spectrum. Understanding this diversity is critical for assessing the potential impact on the habitability of the TRAPPIST-1 system's planets. This research has led to new models for red dwarf star behavior, enhancing predictions about future flare activity and its effects on surrounding exoplanets. The implications extend beyond TRAPPIST-1, providing a comparative analysis with solar flares from our Sun. This is essential for assessing how different stars behave and understanding the impact of their activities on orbiting planetary bodies, especially in habitable zones. Studying TRAPPIST-1 solar flares contributes to our broader understanding of stellar behavior in various solar systems, crucial in the ongoing search for habitable planets beyond our solar system. This knowledge is vital for identifying key factors sustaining life and narrowing down the search for life in the universe. The technological advancements facilitating these observations, particularly tools like the JWST, represent a significant milestone in space exploration and research. This marks a new era in astrophysics, transforming distant stars from mere points of light into dynamic systems with direct implications for our understanding of the universe. Observations of other red dwarfs and their flare activities across the universe uniquely contribute to our comprehension of stellar activities and their impact on exoplanets. These findings